Hello and welcome back to Introduction to General Relativity. In the previous lecture, we started looking at the solutions to Einstein's field equations for a homogeneous and isotropic universe. And in particular, we discussed some qualitative aspects of the solutions that we could infer already on the basis of the general structure of the defining equations of motion. In today's lecture, we're going to solve the equations analytically and then discuss several aspects of these analytic solutions. And finally, at the last part of the lecture, I'm going to introduce the topic of static rotationally symmetric spacetimes. Okay, just to remind you, the equations governing the dynamics of a homogeneous and isotropic universe are summarized here with equations 1 and 2. And these are a set of nonlinear ordinary differential equations. Not partial differential equations anymore, but ordinary differential equations. And you can solve these in a variety of circumstances for a variety of values of k. Remember, k is -1, 0, or 1. And rho and p can be variously positive or negative depending on the dark energy constant coming from the cosmological constant. So we have we can go ahead and solve these equations. We can also use this additional equation that I summarized in the previous lecture. So this equation you can derive by eliminating a from the a double dot from the previous two equations. So if you just eliminate a double dot, you can actually arrive at this equation here. And using this equation, we can already infer a couple of statements about the evolution of the energy density and A. So we have to always consider that there's several models that we could contemplate. One is, for example, the universe comprised of dust, which is like these idealized dots that come from galaxies. And in such a dust-like distribution of matter, that's where the pressure term is 0. So the dots are moving, the little point particles representing galaxies move on the geodesics of isotropic observers. Then this equation simplifies slightly, a little bit, right? And we can realize that that's actually just a total derivative, in disguise. So this is really easy to then integrate. So it's actually a total derivative of the function rho a cubed equals 0, which tells us, of course, that in any such dust-like universe, that rho times a cubed is a constant. And that's good. That's actually really a sanity check on the equation, because what does it tell us? It tells us that that this is just a conservation law, right? In disguise, it's the conservation of rest mass of the dust, because A determines the volume of the universe, and rho the energy density. So you better not have that rest mass has been created or destroyed here, and that's this solution tells us exactly that. Now that's just for the dust-like universe, but there is another scenario that we can contemplate. There's many scenarios to contemplate, but let's consider now the radiation-dominated situation, where rho equals p over 3. And in this case, we find, by a very similar argument, that rho times a to the 4 is a constant. It's just a total derivative argument again. And this looks a little different to the dust case. Is there a conservation of rest mass going on here? Well, not quite, right? Because there is no rest mass for a photon. You can't stop a photon, but of course there's energy associated to a photon. And so here one interprets the result as follows. So the photon number density, right? So the number of modes, photonic modes you have in a volume, well, that scales as the inverse of the volume, right? As a to the -3. And as the universe is expanding, or whatever, contracting, it's getting also, however, there's a frequency component to the photon's energy, and the point is the photonic mode is getting stretched or contracted as the universe is changing, and that actually contributes an additional redshift, a to the minus 1. So hence the radiation hence we obtain this slightly adjusted conservation that I've drawn above here, that rho times a to the 4 is a constant, not times rho times a to the 3. And that's really due to the redshift of the photon. And now that tells us actually something quite kind of interesting, right? Namely that dust doesn't dominate the evolution of the universe in the past, rather radiation does. So as we, in the past of our universe, A went to 0, well, that diverges quicker. Rho times a to the 4 diverges quicker than rho times a to the 3. So the contribution, or the contribution due to the radiation, actually dominates in the past, or dominated in the past. So let's just now specialize. This is a statement that's independent of K. If you take a look at the equation we were solving and the solution, K didn't feature in it, but of course K has got to feature somehow. Whether or not the universe is hyperboloid, spherical, or spatially flat is going to play a role. And now we have to make a bit of a finer case distinction. So if K equals 0 or K equals minus 1, then, and further, we assume we continue to assume that rho and p are greater than 0, then we learn that A dot is 0. And the fact that the universe is, therefore, what do we learn? Well, we learn that that we were in a state of eternal expansion, because expansion of the universe has been established, right? Today we have expansion. And if you observe that you have expansion, namely that A dot is greater than naught, and you're in the K equals minus 1 scenario, then on the right hand side of this equation 1 here, you have only positive stuff. So the derivative in A can never go to 0. In that scenario, when K is either flat, representing the flat spatial slices, or K is representing hyperbolic spatial slices. Further, rho must decrease as A increases. Thus, rho times A squared tends to 0 as A tends to infinity. Now, for K equals 0, this expansion velocity, so A dot represents essentially the velocity of expansion. A dot, that tends to 0 as tau tends to infinity. But for K equals minus 1, A dot tends to 1 as tau tends to infinity. And finally, we can talk about the K equals plus 1 case. For K equals plus 1, we actually have another situation where K equals plus 1, then this negative term here can take over in the right hand side to 1. And we can infer that the universe ends in the opposite of a big bang, which would be a big crunch. Okay, this is still at a qualitative level. Now let's just get the exact solutions, right? And I'll now describe how you can obtain these exact solutions in the case of, say, a dust-dominated universe. And then you'll be able to infer how one can get the solutions for other situations. Now you can rearrange equation 1 to look like this, where c equals 8 pi rho a cubed divided by 3 is a constant, right? The c really here is a constant. This is meant to be big C. Because rho times a cubed in a dust-dominated universe is a constant. And similarly, for radiation dominated, or a universe with only radiation type radiation content, then you also have a similar equation but with an a squared there, where the constant c prime is now 8 pi rho a to the 4. Remember, rho times a to the 4 is a constant. Now, this is a nonlinear differential equation now in A, and you can solve it by standard techniques, right? This is, you work out what the derivative of A is, and then it's an integral, and then you work out the integral and the constants. This is, you can do it, but I'm not going to do it here because this is sort of something that you might encounter already in a nonlinear differential equations course. I won't say that it's super trivial. Like, the integrals are sort of mildly irritating that you have to do, and the answers that you get have a bunch of constants that are buried implicitly in them, and can be a bit awkward to extract this information from the solutions that you find. But it's not, there's no sort of fundamental physical reasons for things being difficult. It's just slightly awkward on a mathematical level. So this eta is a constant of integration that appears when you integrate these equations. So the case of k is 0 is somewhat simpler to derive. There's a little symbol on my notes that I cannot read for the moment. I will just look up the correct answer so I don't write down the wrong thing there. Okay, this is 9c over 4. So the flat case is pretty easy to integrate, actually. You won't have any trouble there. The only difficult ones are the spherical ones and the hyperbolic ones. But once you've done the spherical one, the hyperbolic one no longer becomes a challenge. And then you should hopefully confirm these solutions for A prime. Of course. And you should arrive at a table that looks kind of like this one, up to the labeling of your constants. So this is an enumeration, a case distinction of all the possible choices of K and whether or not you have a dust-dominated or a radiation-dominated stress energy content of the universe. Now these solutions have a name. Well, the spherical solution, or indeed sometimes all, are called the Friedmann-Lemaitre-Robertson-Walker cosmology. And I'll just briefly sketch these solutions for the various cases. So one is this one that ends in the big crunch, that's k equals +1. One of them is the k equals 0, and one of them tends off to tends off to 1, tends off to tau, and that's the k equals -1 solution. Okay, so that pretty much concludes the discussion of cosmology for this course. I mean, there's just so much more that you could say about cosmology and solutions to Einstein field equations, in describing universes, homogeneous and isotropic universes. We won't consider these topics any further in this course, but rather you can use this discussion as a springboard into reading the more advanced literature on this topic. Instead, I want to take our discussion now to the other celebrated solution of Einstein's field equations. So it's really, sort of, roughly speaking, there's two major well-known solutions to Einstein's field equations. One is this FLRW solution, and the other is the Schwarzschild solution, which pertains to static solutions, nothing changes in time, of rotationally invariant distributions of matter or the gravitational field generated by a spherical symmetric body. And in order to write down the solution, I'm going to spend the rest of this lecture talking about what it could mean for a spacetime to be stationary and what it can mean for a spacetime to be rotationally invariant. This discussion will be posed at a level of intermediate rigor. What do I mean? So we'll try and make clean definitions, but I'm not going to bother proving things too much, because in the end this discussion is a motivation for a hypothesis for a metric. So in the end we're just going to write down a metric, and the metric will then be the basis as an ansatz for a solution to Einstein's field equations. And at that point, who cares how we got to it? The metric either solves Einstein's field equations or not, and hence the slightly advanced mathematical preliminary discussion required to sort of derive this form of the metric isn't so important. I mean, the end here is the objective, namely, does this metric solve Einstein's field equations? And if so, what can we learn from that? How we got to that guess, that simplified form of the metric, is helpful for you to know, but it isn't critical, right? It's sufficient to remember the form of the metric. But how did we get there? Well, I'll give you some motivation for this metric, which is based on rigorous mathematics. And firstly, well, if we're going to do something rigorous, we need some definitions. So we got to explore what is meant by the words stationary and static. So we're interested in a stationary, indeed a static solution to Einstein's field equations, one that doesn't change in time. And here, is the first definition that we can exploit to capture this concept. So this is a perfectly rigorous definition now. A spacetime M is stationary if there exists a one-parameter group phi t of isometries whose orbits are time-like curves. And these are somehow the time translates. So that's what it means for a spacetime to be stationary. There's an equivalent formulation. If there exists a time-like killing vector field. That's a different way to say it, right? Now, stationary is not static. So a spacetime M is static if it is stationary and there exists now some additional structure, namely a space-like hypersurface which is orthogonal to the orbits of this isometry group. Now this is a little bit more subtle, the consequences of this definition, and this is where I am going to skip some of the mathematical discussion, but I will say it here in case you want to chase this up on your own. So Fabinho's theorem on integrability tells that this is equivalent to requiring that this time-like killing vector field, psi A, additionally satisfies this equation here. This has got to do with the commuting of parallel transports. And we're not going to prove this here. Because, as I said earlier, it is just motivation. So there are examples of spacetimes that aren't stationary. So de Sitter spacetime, there is not a one-parameter group of isometries whose orbits are time-like curves. De Sitter's counterexample. And there are spacetimes that are stationary and not static. So in coordinates, let's just illustrate now. Just try and now illustrate these definitions and what it means in coordinates. So I'm going to draw big sigma, and a big sigma is this hypersurface, and on big sigma, you can look at this time-like killing vector field on big sigma. Here it is, psi a, a bunch of vectors on big sigma. And these vectors are all orthogonal in a static universe to this hypersurface sigma. And this will allow us actually to construct a foliation of our spacetime. So if psi a is not 0 on sigma, of course it could be 0, right? That would also be orthogonal. So we have to additionally assume that psi a is not 0. Then what we can do is we can build a neighborhood around the hypersurface. We'll call the neighborhood N, and I'll draw it now. So the neighborhood is like this little chunk of space-time around the hypersurface sigma. And then we'll also be able to introduce other hypersurfaces related to sigma by translating the whole hypersurface along the geodesics generated by psi a. So anyway, to begin with, we got this neighborhood N. N is this orange parallelepiped-like thing. So as long as psi a is not 0, then every point of our hypersurface sigma will lie on a unique orbit. And so now we're going to choose some coordinates on our hypersurface, and we're going to extend these to a coordinate system of our whole spacetime. So we're going to label each point P in this neighborhood N, this fattened, thickened version of the hypersurface, by the parameter t of the orbit reaching P and the coordinates x mu of the point in sigma connected to P. So we've coordinatized this fattened or thickened piece of our spacetime. But we can infer slightly more, because this coordinate system isn't generated by just any old vector field. It's generated by a killing vector field, which means it's generated by an isometry. And that means that the metric, if you choose to express your metric in this coordinate system, then the metric components in the system are independent of T. And as sigma t, which is the set of points reached by 5t from sigma, so I'm going to draw sigma t now. Sigma t is like another hypersurface, right? Every point in sigma t is just the image of sigma under phi of t. And as this is an image of a bunch of points under an isometry, we learn that sigma t is also orthogonal to the vector field, the killing vector field, psi a. Or orthogonal to the orbits of phi of t, to make it, to use a language that's consistent with the definition of static. And in these coordinates now, we can actually infer a bit of a simplification for the metric. The metric takes a very particular form, namely ds squared is minus v squared, something that depends on the coordinates of the hypersurface but not time, plus some spatial stuff which is decoupled, there's no space-time components, and what is v, the scalar factor? Well, it's got to be the length of the killing vector field. So we've already thrown out, we got time components, we got space components, but we have no space-time components now, thanks for a static metric. It's already a simplification, right? Instead of looking for 10 things, we're now looking for 7 things, I think, right? 3, 5, 6, 7. 7 functions. So 7 is fewer than 10, but still not like, still quite a lot of things. But we haven't exploited the fact that we're looking for something that's spherically symmetric. This is just static, the metric that I've just written down here, metric star. Let's now take a look and see if we can use spherical symmetry to further simplify the form of the metric. Now, what does it mean, spherical symmetry? Well, again, you know, you look to the symmetries, right? The word symmetry tells you everything. And in particular, for something to be spherically symmetric, it must mean that of all the symmetries that your manifold has, there must be a subgroup that's equivalent to the symmetries of a sphere. So a spacetime M is spherically symmetric if its isometry group, right, that's the group of all its symmetries, contains a subgroup. So there must be a bunch of subsymmetries which are equivalent to those of a sphere. And the symmetries of the sphere is the Lie group SO3, the rotations. And well, there's a kind of degenerate way where that could be the case. And so we want to prevent that. Namely, your spacetime might be just a point, right? That the isometry group sort of degenerately contains a representation, contains a subgroup isomorphic to SO3. So we want to somehow prevent such weird degenerate situations. So we say that the orbits of the subgroup, these got to form submanifolds, and those submanifolds had better be diffeomorphic to S2. The surface of the sphere. And now let's try and deduce some consequences of this definition. Well, the first is that the full spacetime metric GAB, the full metric, whatever it is, because these S2s, these surfaces of the sphere, these orbits of this isometry group are submanifolds now, this metric induces a metric on each orbit. And because of the SO3 symmetry, because of this rotation invariance, because of these isometries, this induced metric, we'll call it HAB, because the full spacetime metric is invariant under these rotations, we must have that the induced metric is a multiple of the metric of a two-sphere. Right? Because there's no other way to have a SO3 invariant metric that induces a metric on the sphere. There's no other possible metric you can write on the two-sphere. That's invariant under rotations. And we could, what is this constant of proportionality? Well, we could label it by the area of the orbit sphere itself. So we can introduce some notation. We could, once we've labeled our metrics on all these induced orbits, we could label them instead by a radii-like coordinate, which is given by interpreting A literally as the area of the orbit sphere. And then we can introduce coordinates on each of these orbit spheres. We just use the metric of the two-sphere, which is unique, the rotation invariant. And now we know that the metric HAB induced on each orbit sphere must look like this. So the picture you should have in mind is, here is a constant time slice here. Take a point P and act on it with all the rotations that come from the subgroup isomorphic to SO3, and then you draw yourself an a sphere S2. So and now we have a sphere. We got we can choose a coordinate system. Just spherical coordinates on this sphere. Now this is in the case where the spacetime is just rotationally invariant but not necessarily static. But now we can put all this together now. So if this spacetime is static as well, and we have to assume that the time-like killing vector field psi A is unique, then this time-like killing vector field is orthogonal to the orbit spheres. And by the way, I should have said, you pick one point, you you apply the isometry group to draw out a sphere S2. Now pick another point that's not on the sphere and say inside, and then you draw, well, another sphere, right? And you can see how by repeating this process for all points on a constant time slice, you foliate your constant time slice with spheres. So the xi's must be, in the case that xi is unique, then these xi's are orthogonal to the orbit spheres. And why is that? Well, if you project xi onto one of these orbit spheres, and then this has to be invariant, but the only vector field invariant on the sphere is that the zero vector field. So that's why xi A is orthogonal to the orbit spheres. And thus the orbit spheres actually lie in sigma t, right? Which is orthogonal to the xi's. Well, now let's put all of this together into to build a coordinate system. And hence write out the metric that we're going to use as our ansatz to solve Einstein's field equations. So this discussion today has all been just motivation for a particular choice of metric. So we start by choosing a fiducial sphere. Just pick your favorite sphere in the hypersurface sigma, and choose spherical coordinates on it. And now we're going to propagate this coordinate system out to the whole entirety of sigma, just as we did for homogeneous and isotropic spacetimes. We're going to take geodesics orthogonal to the sphere to build a full coordinate system or to carry out these coordinates outwards. To other spheres. And so the geodesic parameter that carries these coordinates outwards, we could call it r, the radius. And so we've coordinatized sigma t. And now, combining the coordinate system we have when we described the static universe. So we have the static universe, and the metric takes this very particular form here, star. So combining that with this new coordinate system we're building here, we're going to combine this to build coordinates on our full space-time, labeled by t, r, theta, and phi. And in these coordinates, our metric becomes the following. There's the temporal component, which it depends on the radius. And here comes the spatial component, which has now been highly constrained due to rotation invariance to be effectively just the metric of the standard sphere. And that concludes our discussion of static spherically symmetric spacetimes. If you like, you can summarize this lecture as saying, we hereby assume that the metric has this form written there. The goal in the coming lectures is to substitute this form of the metric into the vacuum Einstein's field equations and to solve for these functions f and h. That's the only degree of freedom left over in this metric, and that's the task to which we'll turn to in the next lecture. But that's it for today. Thank you very much, and see you next time. Goodbye.